So my name is Dante from Ezekiel, which is a suite of tools for basically doing zero-knowledge machine learning. And I'm going to be discussing how you can leverage zero-knowledge machine learning to supplement and complement autonomous worlds. So although zero-knowledge machine learning for autonomous worlds can sound like a pretty beautiful buzzword salad, there's actually a rich history of gaming sort of informing the development of, machine learning and AI. I guess a particularly salient example is the development of algorithms for NPCs. So I would posit that it's actually a pretty natural merger to leverage zero-knowledge machine learning for on-chain games where you care about the verifiability of computation. And we're sort of seeing the beginning of like some interesting experiments in that domain, basically leveraging ZKML for the development of on-chain games. So this is something that Brian sort of hinted at in his discussion. What does a typical ZK app look like? And this is just one mental model for it. There's many, many others. But you're basically replacing sort of like a client-server dynamic with a prover and verifier. And so ZK essentially lets you run really expensive operations off-chain and then prove that you ran them correctly. And the person verifying this can be a smart contract, so not a person at all. And developing in this fashion can basically allow you to encode like more complex dynamics into an on-chain application than you would otherwise by writing everything in, like, say, some smart contract language like Solidity. And ZKML is sort of like a superset of ZK, which focuses specifically on like turning neural networks and other complex computational graphs into ZK circuits. Cool. So and I assume there's lots of you in the crowd that are shape rotators, so this might be easy to understand. So let's say, for example, that you have a smart contract which is governing, like, say, the coordinates for the rotation of a world. I, as a user or as a client interacting with the smart contract, can take in the current coordinates, compute a ZK proof, which updates these coordinates to a new set of rotations and submit that on-chain, and then boom, the world rotates on-chain. Cool. So I guess something also in Brian's talk that was hinted at is that there's been sort of a rich exploration of leveraging ZK for sort of hidden information dynamics in gaming. So things like fog of war, those sorts of things. And I would posit that the main new affordance that ZKML affords beyond like these sorts of, hidden dynamics is the ability to like verifiably compute some pretty complex stuff that you wouldn't otherwise be able to do on chain. So, and we've sort of seen like three main pillars, I guess three sort of like design paradigms arise from like combining ZKML with on-chain games. And the first and sort of like simplest exploration that people sort of naturally reach for is one where the ZKML model is the game. So someone interacting with like the on-chain game is just going to be interacting with some version of this model, and that's going to constitute the entirety of the game dynamics. And I'll be giving examples of each of these categories afterwards. A second, slightly more ambitious sort of design paradigm is one where the ZKML model sort of governs like on-chain physics for the autonomous world. So this might be like some sort of weather model which has been ZK'd and which you can use to like update the weather of some world on-chain. And many players can interact with like whatever this world and state that this ZKML model creates, and sort of like all participate and in these updates. And the third, which is definitely the most ambitious, is ZKML for building narrative or lore for on-chain worlds. So a simple example would be like the idea that like the narrative, for example, might be written by some sort of like ZK'd LLM, and you can basically get proofs that like some pre-agreed upon LLM that you committed to at the beginning when you were creating this autonomous world is indeed writing the narrative of this world. And it can also be used to like create on-chain NPCs, which is what I'll be showcasing after this. Cool. So for this first category, and this is like sort of the simplest thing, and some folks in this room have also built games that sort of follow this design pattern. I think the first sort of like ZKML game was built by Modulus Labs. It's called Leela versus the World. I think it's still live if you guys want to go try it out. We've also built our own version of this design paradigm called Crypto Idle. So in Crypto Idle, what you do is you sing into a browser. You then submit that recording to a model, anthropomorphized as an anime character, which then produces a proof of judgment of your singing. So this proof can either be generated client-side in the browser or on a server if you don't care about the privacy of your voice at all. You can then take that score and the associated proof, submit it on-chain, and you can either get eternal glory or eternal shame based on the score that you received from this anime waifu. If you want to try it out, here's the QR code. All right. So there's sort of an extension of this first model where the ZKML model constitutes the entirety of the game. And it's one where basically if you don't want to encode or code really complex game dynamics, like say, for example, tic-tac-toe or chess on chain, you can just train. This is a terrible graphic. So you could basically take a bunch of like tic-tac-toe state, feed it into a neural network, and train it basically to recognize valid or invalid state transitions. So for example, illegal moves inside a chess game. And so it's a really neat way to like bootstrap game dynamics if you don't want to code them up on chain. You can just leverage a neural network, which acts as a judge as to whether a state transition is valid, produces ZK proof that you've indeed submitted stuff into this model, and that can sort of like basically encode the entirety of the game dynamics. And so we have a really simple example of this, and we'll be actually running through this at our workshop tomorrow if you want to figure out how to build something exactly like this. And we have the tutorial live here as well, if you're interested in this. All right. I see some phones are still up. Cool. All right. So what this previous example sort of hints at is that basically if a neural network is able to encode like the game dynamics, there's actually nothing about like a ZKML library which particularly constrains it to just focusing on ML. If you're able to like take a neural network and compile it into a ZK circuit, you can probably take other complex computations, like say a weather model or some other stuff, and turn that into a ZK circuit too. And so I would posit that most ZKML libraries that are currently out there are actually just sort of like general purpose ZK computation libraries. And they just happen to have started with like neural networks and machine learning. And so this brings us to our second sort of design paradigm, which is leveraging ZKML models for on-chain physics. So in this sort of model, a ZKML model is leveraged to induce state transitions in the world. And as a player, and many other players, can interact with the world that the ZKML model creates. A really basic example of this, which sadly is no longer live, is Baby Gaia, which was created by one of the contributors to our library. And in this world, you have a 2D grid world, and this world is populated with resources, which you can mine. But any player at any time can evolve this world using ZKML. It's not really ML, it's actually just a matrix multiplication of the 2D grid into a new state. But you can produce a proof that you apply this transformation correctly and evolve the world for all other players. Cool. And this sort of brings us to the third and most ambitious category, which is leveraging ZKML for the creation of a world's lore. I guess like a natural thing to reach for would be, for example, to take an LLM or some other language model, ZK that, and use it to write, like, say, the history of a specific world. You could also think of taking some NPCs that you might encounter when you're exploring this on-chain world and then ZKing those dynamics. And that's one of the dynamics that we focused on. And we focused on specifically creating a worm NPC. So there's this paper from some scholars at Harvard and MIT where they create a generative model which takes in sensory data, specifically olfactory data for a worm, and then creates like a voltage map activation for the worm's brain. So we took this generative model and shoved it into a ZK circuit. It was a little bit large, and this sort of served as the impetus for us developing GPU bindings for our library. So if you want to contribute some unused GPUs to keeping the worm alive on chain, you definitely can. So basically what happens, and theoretically, we haven't built Dirt World yet, so if anyone wants to build a sensory environment for the worm in mud, please hit us up. But theoretically, you could take dirt data, which exists on chain, feed it into the ZK'd generative model for the worm, and then post a proof and the new state of the worm's brain on chain, effectively creating a proof of worm that other applications can leverage to build a dirt world with. Cool. So if there's one sort of takeaway that I would want to sort of push on you guys, it's that ZKML is sort of like a plausible candidate by virtue of the fact that it's not restricted solely to neural networks and machine learning for a physics engine for autonomous worlds. And my post-assembly question sort of follows on top of this, which is why should we care about verifiable computation for game physics at all? Thank you.